Yeah, so we start off with the first problem, which is like a short and cute problem, you can say. So it's like a positive integer n is chosen and each of numbers 1 to n is colored red or blue. Show that it is possible to color each subset of each subset from chosen with numbers from 1 to n, either red or blue, so that each red number lies in more red subsets than blue subsets, and each blue number lies in more blue subsets than red subsets. So, okay, the problem statement is nice. And so basically, if we look at, say, the case where there is only one red number, then there are like 2 to the n minus 1 subset it belongs to. And so we'd want that like 2 to the n minus 2 plus 1 subsets, at least like these many subsets should also be blue. So there is this one idea, like a sort of cheap intuition that you can call, is that if there was some red number that was along with the blue, like the single blue element, in say all of its blue subsets, then that red number would be in sort of trouble. Did you get like, do you get what I mean? Like say there are 2 to the n minus 2 plus 1 red subsets that a blue number belongs to, and say that there is a red number which also belongs to all of these subsets, then this red number is sort of in trouble because it already now belongs to 2 to the n minus 2 plus 1 blue subsets. So which are like more than, do people like, is it clear like why that is problematic? I guess that is obvious, but so this sort of gives an intuition that if say like there are say x, should I use a minute? Yeah, say like 1, 2, 3. Yeah, so 1, 2, 3 till k are all the red numbers, and say these each of them belongs to say x1, x2, xk blue subsets, like the subsets which contain it but like of the opposite color, then x1, x2, xk should be sort of close to each other. uh, like is that clear, I guess? From that like case where there was only one blue element, because if one red element is in a lot of like is in a lot of blue subsets with that blue element, then it itself is in danger, because then it isn't in enough red subsets. So these x1 to xk should be sort of close to each other. Like, do people get it? Can someone say?
Yeah.
Yeah. So now, like, you guys can think for some like 2 to 3 minutes, some sort of an algorithm that brings these x1 to xk closer to each other without like affecting other things. But like, you can try not to affect other things as much. So I can repeat once more. So I assumed like 1 to k are like all colored in red, and this x1, x2, xk denotes like the element I belongs to xi blue subsets, that is the subsets of its opposite color. And so we are claiming, like, obviously we want this to be less than half the amount of these subsets it is in, but we also claim that these should be kind of close to each other by looking at the example where there was only like one blue element, because I guess you get what I mean. Yeah. So, do anyone have like? Does anyone have any ideas? Okay, then I'll proceed, I guess. Yeah. So suppose like we have two elements I and two red elements obviously, and say xi is less than xj, then what could possibly be happening? So we so xi and xj denote the number of red subsets the number of blue subsets I and j belong to. So if we look at a blue subset, it contains both J and I, then like that doesn't really affect us because then we are looking at how these are differing. So we need to look at blue subsets which contain J, but they do not contain I. So now we want to sort of biject it, like a subset of that kind with some other kind. So like we can do some algorithm and maybe sort of switch them to like increase we essentially want to bring them closer, we want to be increasing xi. So to to proceed along these lines, what we can think of is, say we consider a subset A such that j like this j belongs to A, and this subset is a blue colored subset, right? So what we can sort of biject, like I doesn't belong to this, so what we can sort of biject it is with a set uh, yeah, B, which I belongs to, but like J doesn't belong to. So this B that we created is basically essentially like taking A, removing J from it, and inserting I in its place. Yeah. So if like I claim that there will be a subset such that this case where like J belongs to A and A is a blue colored subset, but like this sort of the set B that I created by essentially like taking A and then removing J from it and inserting I in its place, this element B will be a red element subset, and then I will like essentially switch their colors. So this sort of increases xi by 1 and xj by 1, but now it remains to see why it happens. So basically, we are ignoring cases where I and j both belong to the same set because that doesn't really contribute to difference xj minus xi. So whenever it happens that j belongs to a red subset A, and I does blue subset A, but I does not belong to it, then we mark like we biject this with a set a B or A prime, you can say, which is essentially just taking out J from it and inserting I in its place. So to keep count with this, essentially when we are this creating sort of bijection. So since xj is greater than xi, it should follow that we should not be able to do such a bijection. And in that case, it would follow that uh, I belong like this B that we created is not a blue subset, because otherwise like xi you can like you should be able to stop when you're comparing xg and xi. But now notice that B is a red subset, A is a blue subset. So if we switch the colors between these two subsets, then the following happens. Any other color is not affected because the only elements in A and B that were switched were J and I. So the other quantities all remain constant, and it happens that now blue like J is in a less blue subset and I is in more. So this sort of increases xi by 1 and decreases xj by 1. So essentially like this will be bringing them closer unless they are like unless mod of xi minus xj is less than 1, less than equal to 1, we can always perform an operation on xi and xj and bring them closer to each other. Do people get this?
Yep.
Yeah.
So like now we also need to prove this algorithm stops in a first place. So like this is easy because note that whenever like if this process were to be performed indefinitely, then notice that whenever you can perform a move on xi and xj, then like if you consider like at each step you're looking at the values x1 till xk, and then you're looking at the minimum of these values, right? So whenever you can perform and move on xi and xj, you can also perform a move with, say, the larger of those two and the minimum of those two. Do people get it? Like, because that difference will obviously be uh, greater when like, okay, so let me actually plot this. Say this was xj and say this was xi, and these are the values which are like at the minimum level. So notice that whenever this difference is less than equal to 1, obviously this difference will sorry, whenever this is greater than equal to 1, this difference will obviously also be greater than equal to 1. So whenever I can perform a move involving xi and xj, I can perform a move that involves m and xi. But then notice that essentially one of these values that was here gets increased. So eventually this M line has to cancel off and eventually the process will stop. Do people get it?
Actually, can you repeat it once?
Yeah. Like, did you get like how we were, if the difference was greater than one, then we would perform a move and they would be closer to each other because xj would decrease by one and xi would increase by one.
Yeah, I got that.
Yes. So basically, now we want to prove that we cannot perform this indefinitely, and so we'll uh, like achieve a configuration wherein any two, the modulus of the difference is less than equal to 2. So to prove it, at each step, like xi changes, but we note the minimum value. So like these are basically the values plotted, so it becomes easier. So then these are the set of values of x1 to xk, like the subset of these which achieve the minimum value. So now notice that whenever you perform a move, say involving xj and xi, and xj is greater than xi, then you can also perform a move with xj and a minimum element. Do you get it? Because that difference is obviously greater than this difference.
Oh, right, unless they're all the same.
Yes. So like not about, yeah, I mean like there are only two levels. So yeah, so eventually this minimum line will vanish and all of these xj's will be pretty close to each other. So I guess that is, so let me erase this. So similarly, if I now define a quantity, say there are like m blue elements, and for each blue element, I define this quantity yi, which so yi denotes the number of, like similar to xi, yi denotes the number of red subsets a blue element belongs to. Same to it, I can perform the same move. Notice that like whenever I perform a move on xi and xj or y or yj, all other x quantities and all other y quantities remain invariant because of that thing we bijected it. So all the elements were like present in A and A prime as well. So it's just like one thing. So their quantity remains unchanged. So I can similarly perform this expression, algorithm, such that yi minus yj mod is less than equal to 1. So at this point, since all these are pretty equal, we so ignore that the null subset, its color doesn't matter. So there are like 2 to the n minus 1 subsets in consideration only. So we color in like any 2 to the n minus 1 subsets blue, and any 2 to the n minus 1 subsets red. Like also we are assuming that say there are key red elements, m blue elements, and k is at least m, and this is greater than 2. Like essentially the problem has a very nicer solution in my opinion, but this was a approach I thought which was sort of motivated in my opinion, and it had a nice idea, so I was presenting this. But like so with this value we can like so if there were k then and m, so the maximum value, if I look at the maximum, sorry, the minimum, yeah, the maximal. So the maximal value, if I look at say sum all these, then there must be a red element which belongs to, sorry, which belongs to at most 2 to the n minus 1 upon k elements. Do you get it? Like that's just pigeonhole, I was unnecessary confusing. Uh, this is easy, right? Like some element is in at most these many subsets.
Yeah. Like
Yeah.
some red element, right?
Yeah.
Right.
And then this quantity is also less than 2 to n minus 1 by 3, which is also less than 2 to the n minus 2 minus 2. So basically with this, this holds for, this obviously holds not for every n, but like the n I have taken, that works. So with this, we have proved that like, so one value we have got that will be less than equal to this expression. But since due to this algorithm that we performed, every value, so the maximum value that it can be is of, so 2 to the n minus 2 minus 1, like the modulus thing. So this is actually good because each element was in 2 to the n minus 1 subsets, and each red element now belongs to at most 2 to the n minus 2 minus 1 blue subsets. So we are good to go.
Makes sense.
Yeah. So obviously this is like a tiny issue because obviously m will not be greater than 2. But to counter this, what we can do is basically perform the same algorithm. I won't be repeating it again because it is unnecessarily complicated and I get confused myself between red and blue. But you can do is like m is the number of blue elements, and so except like y and yj denoted the number of red element, yeah, the red elements, red subsets that each blue element belongs to. But when this is the case, so we'll actually reverse the like use of y and yj, and that will also work because now we can, and instead we'll just change the coloring a bit. We can do 2 to the n minus 1 plus 3 of one color and 2 to the n minus 1 minus 2 of the other color. And since like here we were using the fact that this was like less than equal to this, but when m is small, we can also make sure that this expression is also large enough. Uh, should I leave it, or like do you like basically essentially you just need to change what yi means and then do the same argument, and because we can find like do this pigeonhole type argument, and because like they differ only by at most one, so you'll be good to go. I find it unnecessarily confusing to constantly repeat red and blue. Basically the point of me trying to put out this problem was to show that this nice enough algorithm works xi and xj. If the difference is less than equal to like, then you can like if it is greater than one, then you can switch these and they increase, and essentially that works because then they are close to each other, and something is in these many bad subsets, but since they were close, so everything works fine.
Did you spot the algorithm in practice?
What?
Did you spot the algorithm in practice?
Yes, like the official solution for this is quite simpler and quite nice. Like essentially, yeah, I was trying like xj and xi, and then sort of this idea of why these differ, and like basically that cheap intuition I highlighted in the beginning about when we consider one element, then the number of bad subsets each color is in, they are quite close to each other. So I was trying this xi and xj thing, and then like sort of then obviously it's easy to see that if both are present in the same subset, we don't need to consider those. When it is not, then we sort of want to biject it with some other thing which must be of the opposite color, so that I can like switch the colors there and sort of bring them close to each other. And also like I'll present the official solution, which is like much nicer. One of the official solutions, one is also like not direct induction, but induction with a stronger hypothesis sort of works, but this one is much nicer. So basically what you're doing is you're like assuming the number of blue elements is greater than the number of red elements, and obviously there must be like at least two blue elements and at least one red element. So now what you're doing if is you're considering all the subsets, and a subset which has even length, you're coloring it red, and a subset which has odd length, you're coloring it blue. So like each element belongs to 2 to the n minus 1 subsets, and it also belongs to an equal number of odd numbered subsets, and it also belongs to an equal number of red element subsets. So it is in 2 to the n minus 2 red subsets till now, and 2 to the n minus 2 blue subsets. Now what we are doing is, so this also sort of, I guess, was motivated along that same intuition that I highlighted of picking one color and noticing that these quantities have to be close to each other. So 2 to the n minus 1 there and 2 to the n minus 1 there. Sort of, I guess, maybe motivated by that. But now we are like, so each element till now is in 2 to the n minus 1, 2 to the n minus 2 blue subsets and 2 to the n minus 2 red subsets. Now comes the major part. So what we'll do is, if a subset contains entirely blue elements, we'll paint it blue. And if it contains entirely red elements, we'll paint it red. So initially note that even length subsets were colored blue. Was it colored blue? No, yeah, sorry. Even length subsets were colored red. So now notice that any singleton set consisting of a red element will now be painted again to red, which was initially blue. Do you get it? I might have complicated in saying this, so I'll repeat in trying to simplify it. So we start off is we basically paint any subset which has even length red and any subset which has odd length blue. Every element is in an equal number of odd length subsets and an equal number of even length subsets. So every element is in 2 to the n minus 2 red subsets and 2 to the n minus 2 blue subsets. Which and now what we are doing is we are modifying this a bit. If a subset contains entirely red elements, we are painting it back to red, irrespective of the length condition. And similarly for blue. So now it happens that if you consist of singleton sets containing red elements, then initially they were odd numbered and so blue, but now we painted them back to red. So they are red now. And similarly, since we assumed that there were two blue elements, at least two blue elements. So any blue element, you can pair it off with another blue element and look at that two element set, and it will again be converted back to blue. So this increases the number of red subsets each red element is in, and the number of blue subsets each blue element is in by at least one. And so we are good to go there. Do you get it? Like
Yeah,
this was
makes
the
sense.
official
Yes.
solution. So we'll sort of move to the next problem. The reason is yeah. Okay, so the previous problem was from a mock JMO and it was P5. In some countries, several pairs of cities are connected by direct two-way flights. It is possible to go from any city to another city by a sequence of flights. The distance between two cities is defined as the least possible number of flights to record. It is known that for any city, there are at most 100 cities. The distance 3 from it. Prove that there is no city such that more than 2550 other cities have distance exactly 4 from it. So obviously it is like the first statement just means that the graph is connected, and the second state, yeah, it's just the normal distance.
Why connected?
Like it is possible to go from any city to any
Okay.
sequence of flights. So essentially, like this is connected. So we'll start off with the case where it is a tree, because like the notion of distance works very fine in a tree, because say if you root it at some vertex and then you look at say the branches that arise out from it. Yeah.
The third statement gives a motivation for three.
What?
The third statement itself gives
Yeah,
a
like
motivation for a tree.
like you're considering distances, and if you look at a branch, then the notion of depth in a
Yep,
branch
yep,
is
yep.
quite well defined. So obviously They're like
And the third statement gives like a motivation to consider like a tree.
yeah, so just drawing it out. And so like it's easy to see that so due to this good enough definition of branches, we can say in each branch, like suppose there were x elements in this branch that were distance. So we sort of want to sum this x over all branches and sort of try to bound it. So there comes a very short observation that will solve this in the case of a tree, and that is like using this condition that there it is known that for any city there are at most 100 cities at distance exactly 3 from it. So so we
Like
sort
from
of
a point, we can have at most 100 branches.
what
Like from the topmost point, we can have at
yeah,
most 100
yeah,
branches.
like that is obvious, but you need to sort of bound x with respect to something, right?
What is
What is
x
X?
defined to be?
Like
See,
x is like I just considered one branch and the vertices that are a distance 4 from it.
okay.
Like
Okay.
but okay, that doesn't give anything on x, so we need to, and the trick to solving this, that is like looking at the first vertex of this branch and then noticing that also like I'm considering only branches that have length at least 4, because otherwise it's futile to look at it because there won't be any x, like x would be 0 for that branch. So if I start off at this vertex, then notice that this thing works out nicely. This vertex, and this one, two. So this is at distance 3 from it. And similarly, on each of the remaining branches, I can find a vertex that is distance 3 from it, from the top vertex. Do you get it?
Yes.
Yes, and this sort of allows us to bound x with respect to the number of branches, because now we have that, like for one element, like
Like we at max have like 100 branches from point to point.
yes, no, like that is true, but wait a minute. So basically, if I look at this,
Wait, I have a bounding idea, I guess. Like
what?
from the topmost
Huh.
point, we can have like at most 100 branches, right?
Hmm.
So that each of those 100 branches, like we consider the point on each of those branches, which is exactly 3 distance from it.
Hmm.
So we need to find like we need to have like a point beyond that branch. Then
Hmm.
only we can get in points is that it has exactly 4 distance from it.
Hmm.
So like from that point, we can at most have like 99 branches from the down points, because like we can,
But yeah, like I get it, but how does that help to bound x with respect to the original, the vertex that we
like
have?
then we can
What is
get the
X
number of
again?
x. We can,
Like the vertex I rooted at, so the number of vertices on this branch which are at distance 4 from
like then
You
we can get
speak too
the,
fast. Can you slow down a bit? What did you say? X. X is what?
it. Like if I consider the root, then I look at a branch from it, and then
Okay.
a vertex that has, so the vertices which are a distance 4, these two.
Distance 4.
Yes, like
Okay.
as mentioned here, 1, 2, 3, 4. So like these two vertices, so x is equal to 2 here. Basically, x is the number of vertices in that branch which are at distance 4 from the vertex we rooted it at.
but that bounding idea says because like the number of cities become greater than 2550.
No, but like x was respect to this route, and your idea is like to proceed on one branch and then looking at how many more branches that can be, but that does not relate very nicely to x, right?
We can consider the what is that called? The node just below the rooted node.
Yes.
With that, you'll just only have like what? 100? So x is also less than equal to 100.
Okay, nice. But can you think of like something stronger?
Oh, okay. 3.
Like the idea is essentially to consider this vertex only, but like that 100 is a weak. Look at more vertices that are distance 3 from it.
The other
Ah,
nodes.
Yes,
yeah,
yes. Like
yeah,
the
yeah,
distance 4 vertices, these other x minus 1 are also distance 3 from it, right?
yeah.
So we'll have this bound that x plus,
X plus something is less than equal to
like x
100.
plus the number of branches, basically minus 1 is less
1
than equal to
minus
100,
1.
right?
Yeah.
And then like this pretty much finishes this because then, yeah,
Wait, that is less than or equal to what?
100.
Okay.
So we'll have that each, like say x is less than equal to 101 minus b, and then if you sum it up over all branches, then the entire thing that we were looking for is less than b into 101 minus b, and this is a quadratic, and this is maximized when b is say 55, right?
What?
Like for each branch, the number of x like which are at distance 4 from it is less than 101 minus b. The b is the number of branches, right? If I sum
Yeah.
that up over all branches, basically those are vertices that are distance 4 from it. So the thing is less than equal to b into 101 minus b.
Ah, okay.
And this is a quadratic, and this achieves its maximum at say 55, no?
In between.
50. Yeah, for integer thing, 50 into 51. And I guess that is 2550. But this is just an equality case, and we were trying to motivate stuff. But this is quite nice. The equality case is
What is B again? Can you just tell me?
b is the number of branches from the original root.
You're he's considering b as the variable for a quadratic equation,
Yes,
and
and
then
b into
maximizing
101
that.
minus b, yeah, like b into 100 minus b is a parabola, and that is maximized when b is 50, like for integer b, right?
Like that is I get the sum of maximizing. But how do you get this inequality? Like x plus b minus 1 is smaller than equal to
Oh,
Oh,
b times n.
that. So basically, like as Himadri pointed, you need to consider this first vertex here, and
Yes.
then you look at vertices at distance 3 from it. On each vertex, there will be one, on each branch, there will be one vertex such, right? You agree?
Yes, yes, yes.
And the vertices at that, like the x minus 1 vertices, which were distance 4 from this, are also distance 3 from this.
X minus 1.
So
So
actually, I should write x minus 1 plus b. That would, I guess, help more.
wait, why is x minus 1 like
b
say
minus
distant
1
from
is
it?
fine. No,
What? Like
b
x minus
minus
1, like x minus 1 tells this x minus 1 vertices, and the other, oh sorry,
okay, yeah,
b minus,
that is.
wait.
Oh yes,
You
yes.
have
Okay.
you have b minus 1 other
Yes, b
branches.
minus 1 and that
Yeah.
vertex itself, so x plus b minus
Yes.
1, and this works out. So we see that this equality case is actually quite powerful, and the only thing that we used here was the notion of branches and the notion of depth here. So in sort of any connected graph, so now we'll try to optimize the case of any connected graph into this. So I'll let you guys think about it for some time. Because like you can see, this equality case is already very nice enough, and this notion of branches relating to distance is also nice because we can root at a vertex and think. So yeah, like think about optimizing the case of any connected graph into this.
Can we take some sort of like BFS graph? Like, let's say there was a vertex with
Mhm.
more than 2550.
Mhm.
We take a BFS tree
Mhm.
and like you get essentially the same structure except like there are some issues with
Yeah, like basically there are some cross edges that can be possible, which sort of don't allow us to basically.
Yeah, but then I was thinking, what if we do like reverse BFS or something?
Hmm.
So like we join the ones with like which are the farthest away first or something like that.
Okay.
I'm not sure. Let me think.
Hmm. Any ideas more like how, like the basic point left in the problem is to take any connected graph and say root at it, and then basically trying to transform that structure into this, because we need this notion of branches and we don't want edges to go from there to there. So so that we can repeat the same bound, like bound.
Like to maximize the number of cities, distance 3 or 4 from it, we need to consider a tree only, no? In those other cases, it will not maximize, like a tree maximizes.
But like why?
Because like tree has some branches. In a sort of a connected graph, which is not a tree, you don't have like something like branches that just increases
No,
the
this
number of points
bounding
with
needed,
a
yeah, like this,
certain distance from it.
but like this notion of branches was important in order to bound it, because there can be stuff like there to there, and there you cannot necessarily see, you'll like
Yes,
say find something, or like the like the distance from this vertex to, like obviously this will always remain 3, but the other cases wherein you're trying to find a vertex at distance 3 from it. So okay, I'll proceed then. Uh, hmm. So essentially, we'll obviously pick the vertex which maximizes the number of vertices at distance 4 from it. And so that like we only like care more about vertices which are distance 4 from it. And like in this structure, what was something that was beyond this 4, we don't really care about it, because firstly, this is distance 4 from it, and vertices beyond this are greater than distance 3 from it. So vertices that are like greater than depth 4 are pretty much useless to us. So even in the new graph that we will try to create, we'll want these, we'll want these vertices that are at distance 4 to act as leaves again in order to simplify stuff, obviously. So uh, what we'll do is we'll like algorithmically just add paths from say, so we'll consider this set of vertices which are like at distance 4 from V, and what we'll do is we'll algorithmically add paths from there. So um, And notice that we are like not creating an induced subgraph. Like we are not necessarily including all the edges and say like you'll okay, let me tell this first and then we'll elaborate that. But yeah, essentially we'll be just adding say paths from there, unless so we want vertices to occur only once, like in one branch. That is all we want, and that is actually pretty simple to create because you say like you're say suppose you were adding paths continuously and you'll be stopping when to like some of these like okay, let me draw it. So say I was randomly just adding paths from here at distance 4 till they did not intersect. So like I did this. I was randomly adding, but now the issue is that there are some vertices which were already there. So that's not an issue actually, because if these some of these vertices coincided between them, then you could just continue that path. Uh, do you get like what I mean?
I don't get why that wouldn't be an issue. Like, can't you go from one branch to another branch to again another branch?
No, like we are avoiding that. Like we are avoiding cross edges. We are ignore. This is not an induced subgraph. Like this does not include all the edges between the vertices already present.
Also, like, we're trying to construct a subgraph and then we'll try to show that, like, it can't be better than this subgraph. Like,
Mhm.
right.
So this is like we are ignoring obviously edges. Like for example, could be this, but it's just essentially trying to show that whatever bounding work there would work here. But yeah, so we'll be just adding these paths from that vertex to this vertex. And if a path intersected, then it must have been a part of this branch and we'll just extend it. Do you get what I mean? Like if the path was not completely a new thing and this vertex that was added actually intersected with some of this, then we'll just attach it to there. Do you get?
Right. So, like, let's say distance is 4, we just connect it to the nearest third
Yeah.
one.
Like, would you repeat? Yeah,
Like,
like,
that's what you're saying, right? That if I have
uh,
something with distance 4,
uh,
I just connect it with the nearest third, like,
uh.
distance one.
Like yeah, okay, that is true. Like we is essentially we don't care about crossing edges now. We just want these to be in separate branches. So if you so like if we have created this new graph, you can say, and the bounding that we needed for that. So like if we look at direct neighbors, or what we can say the parent of each branch. So these vertices are distance 1 from this, and these end vertices 1, 2, 3. So these such vertices are distance 4 from it. So the distance between them is still 3. Do you agree? Like this distance was 4, and since this was a neighbor of this distance will actually still be 3, because if it was less, then this wouldn't have been a distance 4 vertex in the first place,
Yeah.
right? So the only sort of issue with bounding is, are we able to find a distance 3 on each other branch like we did in that case, right? Because these are still distance 3 from that. And so now we show that we can actually do, because if we consider the endpoints of a branch, and since we ignored anything beyond, the endpoints of a branch are distance 4 from it. And notice that, and among these three vertices, yeah. So if I consider these three vertices, like the endpoints of each branch are basically vertices at distance 4. So if I look at the topmost vertex or the parent at each branch, like I did in the previous case, I want to ensure that there is like at least one on this branch, which is exact distance 3 from this vertex, right?
Right.
So, but that is obvious only because if like the distance was less than equal to 1 or 2 somewhere, then this won't have been a, like, if I consider this thing, and if the distance between these two vertices was say less than equal to 3, then this won't have been 1, 2, 3. So yeah, basically this one. If the distance was say less than like was 1 or 2, then yeah, then this wouldn't have been a 4 distance 4 vertex in the first place, because I could just write down along this and then go there and go there in less than equal to 4 steps. So like it was so-called optimization, but there is nothing actually after solving that case, because this is just a way of looking at it and still ensuring that on each separate branch that we have created, we can still find a vertex that distance 3. Do you agree?
Yes.
So like it's the same as the previous thing. So we are done with the problem.
Source.
What?
Source. What's the
This
source?
is 2013 C6.
Okay.
And so we'll move on to the next problem. Yes, this is, yes. Let n be at least 3 be an integer. In a country, there are n airports and air airlines operating two-way flights. For each airline, there is an odd integer m and m distinct airports C1, C2, Cm, where the flights offered by the airline are exactly those between the following pairs of airports C1, C2, and till Cm and C1. Prove that there is a closed route consisting of an odd number of flights where no two flights are operated by the same airline. So let me translate this actually. So these are like you have a graph with say n vertices, and this is not necessarily simple graph. You can allow, like as the problem statement says, you can allow multiple edges between two vertices. So it is saying that you have a graph n and its edges are colored in n colors, and the condition here is given that the edges formed by each color, if you look at the edges formed by each color, they form an odd cycle. And then you need to prove that you can find an odd cycle where each side is a distinct colored, uh, is distinctly colored. Do everyone get the problem statement?
No.
Then really for
Can you
support.
repeat?
Okay. Okay. So basically we have n vertices and the edges between them are colored in n colors. And for any color, if I look at the edges, then the edges are in an odd cycle and nowhere outside it, right?
Okay.
And so we essentially need to prove that uh, there is a odd cycle in which all the edges are different colors. Does everyone get it? Go browse with the
Yeah.
So, so to start off with this problem, so I was essentially G solving this problem with my friends, and
Me.
okay, you're not a friend, but
Damn. Okay.
so so essentially what I started off with was, if I, like, we can sort of assume connected. Well, if we'll essentially realize that there isn't much use of this statement, but okay, it provides a good base to start with. So basically, if the graph was not connected and we partitioned it into several connected components, and so I guess I should draw more. Say the graph looks something like these many separate connected components, and uh, so any cycle, like due to these are like connected components, so any cycle forms an so every color forms an odd cycle, And notice that the cycle must be contained entirely inside each of these connected components, because otherwise, like that is the definition, because if there was an edge between these two, so that would contradict somehow. So suppose that if this has, if this consists of C vertices and Ci different colors are present inside it, then we know that the sum of C is equal to N and the sum of Ci is equal to N. Then we would get some condition such, then we would get some connected component such that Ci is at least C. Do you agree?
Wait, can you repeat?
Yes. So, did you agree that an odd cycle must be present entirely inside a connected component?
Yeah.
So basically, if a connected component has C vertices and Ci different colors present inside it, so there are n colors and n vertices, na? So if I sum, so if there was like that Ci was strictly less than C in each of these cases, then summing over all them, then we would get that sigma C is less than sigma, sorry, sigma Ci is less than sigma C, and which would be a
Right.
contradiction as both
Yeah.
were. So, but now in this case, we can just induct, right? There are n, like there are at least n colors here and n vertices here. We can ignore some extra colors, and this is essentially satisfying the same condition, right?
Yeah.
So we can assume that the graph is connected. Now we'll see that this doesn't have actually has to do much. So at this point, one of my friends suggested that we should think of us like we'll call any structure that has different colors rainbow, because he said that it is called rainbow. So he said that obviously with connected graphs you can think of a spanning tree. So he said we should think of a rainbow spanning tree, like in like n-1 edges, all of different colors. Like obviously this is too much to ask for, because the graph should behave very randomly, that you should not be able to
Yes,
find.
obviously.
Yes, but I guess that was some friend who thought that there should be some rainbow spanning tree, but okay, that doesn't exist. But at this point I actually, oh, like which terms did you not understand, Anurag?
Like just leave it, and I don't really understand much of graph theory.
What?
I don't really understand much of graph theory, so just leave it.
Like,
I'll
no,
just
no,
try
like
to
which
understand.
term did you not understand? Like there isn't any graph.
Spanning trees,
Okay,
nodes,
spanning
roots,
tree.
edges.
Okay,
There are very really much things I don't
like,
understand in graph theory.
okay, but like edge, you understand edge
Yes,
obviously,
yes, yes, yes,
and degree, you understand the number of edges.
yes, 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 yes.
So leaf is basically a vertex with degree 1, and in that problem, that previous problem we did, basically the endpoints of a branch were degree 1, na?
Yes,
So
yes.
these are called leaves, and basically no use of them. Like okay, these are just notational terms. And spanning tree is basically, do you understand what a tree is?
Yes.
Okay, then a spanning tree is just which a tree which includes all of these vertices. And that friend suggested that we should think of a spanning tree in which all the edges were differently colored, because with connected graphs comes with this thing of spanning trees, you know, right?
Yes, yes.
Yes, so we suggested obviously that is too much to ask for, because these graphs should behave very randomly and you'll not be able to get this very good condition. But let's think about it. So essentially, when we have a tree in
I
which,
was asking, like, is just light gone at your place?
yes, what you can say,
Okay. Are you
This
working
looks
from Wi-Fi or
nice.
some mobile data?
no Wi-Fi, USB, what is that called? CP,
Oh, yes.
UPS.
UPS.
Yes. So, yeah. So let's look at a random tree and say that all the edge colors are of different colors. Then notice that these are n-1 edges and n vertices. We are just assuming that we have a tree, and let's see what happens. So one color is left out, and that one color forms an odd cycle as given by the condition. And the vertices of that odd cycle are like the vertices of the tree. Do you get it? Like that color is not present here. This is it. say simply this was that triangle. This is the I'm not changing colors because that is too much of an issue, but this triangle that I formed now, this is of a different color. Okay, so we know that it exists and it forms an odd cycle between some of these odd number of vertices. Now we would be done if suppose this distance, if this distance was even, then this, like we know this is a rainbow spanning tree, this edge is different color, this edge is different color, and this edge is of different color. So okay, so so this would have been our odd cycle. So this doesn't happen, which must imply that, okay, so I'm defining this term called distance between these, which is basically you take the shortest path between them on the tree and then count the number of edges between them. So here say the distance is 2. You get it between these two vertices? Anurag, like since you don't. Hello. I guess you didn't listen. Yeah, so if this distance was even, here two edges, and this is the third. So this would have been our rainbow cycle, rainbow odd cycle, basically the odd cycle with 3 different colors, right?
Yes.
Yes, but this doesn't happen. So this must imply that if I define this, like if I consider say x1 and xn were like the vertices on the tree, then oh no, like sorry, this like the vertices on the odd cycle, if they were x1 till x1, x2, x2k plus 1, these were the vertices of the odd cycle of the color not present on the tree, right? So the distance between any two consecutive of them must be odd, right? Because otherwise we already have this. Let me draw it. Say like, I'll explain. Say if there was some, like if these were vertices present in a cycle 1, 2, 3, 4. So the distance is even, and if this was something like this, if the distance was even between these two vertices, then this would have been our odd cycle. So this doesn't happen, right? Do you get why like the distance between xi and xi plus 1 should be odd? Otherwise,
Yes.
you already have your
Yes. Yes. It is the correct.
cycle. Yes, you already have your cycle. So we get that d of xi and xi plus 1 is even. I'll just work in mod. So I'll just write equal to 0. Oh, sorry, odd. 1. So we want to bring sort of a contradiction because by the problem statement, this is a very nice case. So obviously there must exist an odd cycle in here. So we should try to somehow think of distances. So now comes this great notion of distance on a spanning tree. Basically, there is this thing called a skeleton of a tree, which is basically the number, like the path of longest size. So I'll just draw it. So if I consider this, and then say this was a spanning tree, then the skeleton is basically this, right? So the notion of distance is very nice in a tree because if I say I have a vertex A and a vertex B, and say this, it is connected at the skeleton at vertices V1 and V2. So basically the distance any like bit, also we allow distances to be 0. Like distance between same 2 points is 0. Like this will help for notational convenience. So this must imply that the distance between A and B is basically you run down the branch to the skeleton, then you move along the skeleton to reach another branch, and then you ascend or descend up that branch. So this should be d of d of a v1 plus d of v1 v2 and d of v2b. Everyone agrees? Like that. This is the good thing about you have a very long path, then you have the notion of branches, then you need to come down a branch, move along the skeleton, go up a branch, right? Hello.
Yes.
So what I'm trying to prove now is I know like okay, this is also one more thing about distances. So yeah, if I consider vertices that are on a path, like not on different branches, but 3 vertices on a path, say x1, x2, x3, right? So we have this thing that between any two vertices, I can write it like this, like d of x1, x2 is equal to plus minus d of x1, x3 plus minus d of x2, x3. Does everyone get it? Like you can think about it for some time. Any like between any like any permutation of 1, 2, 3 between any x1, x2. You can write it like this if they are on a path. Like basically x1, x2 is x1, x3, and then you subtract x2, x3. So and for a general case, you can write it as plus minus because this will allow us to work in mod 2 because plus minus don't really matter in mod 2. Hello. Hello, bros.
Yes.
Like, does everyone get it? Because no one is saying yes or no. I'm sad.
Like we all are waiting for each other to say yes, then we all say.
What?
Like most of us are like trying to wait
Yeah.
that someone else says yes.
Okay. So with this, you can actually write between any two vertices A, B, C on a path, d of A, B is equal to d of BC plus d of AC mod 2 because plus minus doesn't really matter mod 2. So, and this will help us because we are essentially dealing with an odd length, even length condition. So this is a very specific case. And now when we are trying, so what I'm trying to prove is in this case, x1, x2 is odd given by condition, x2, x3 is odd. If they were on a path, then x1, x3 would have been even, right?
Yes.
Yes, that is true. So essentially wanting not simple, and so I would be looking for an edge, and this distance should be. Oh yes, yeah, I get it. Oh, I could confuse myself, but now we can work in mod whatever. So basically, yes. If I look at, so I'll induct basically on, like we know that x1, x2 is odd, x2, x3 is odd. If they were to lie on a path, this x1, x3 would have been even, right? So I'll try to prove it more generally. We'll claim that d of x1 and some even number x2m is equal to 1, like x1, x2 was 1, and d of x1, x2m plus 1 will be 0 mod 2 in a general thing. So suppose that it was, so now we'll be just exploiting this condition, these two things. Basically, we'll for any three vertices, we can write this as a combination of like going down the branch, moving along the skeleton, and moving up, and then using this fact that I can also write this as mod 2. So if I look at x1, I'll just mark them screen of graph. Suppose like this one was x1, this was, I'll prove it by induction. So this was x2m, and we want to show that, and say this was x2m plus 1. Right. So now we'll consider their point of attachment on the skeleton. Like it is quite evident that the skeleton is the horizontal one. So, and I'll call these v1, v2m, and v2m plus 1. So I guess you might even be seeing why, if I assume that x1 till x2m is equal to 1, and given by the condition x2m and x2m plus 1 was also 1, so x1 till x2m plus 1 will be seeing, but we need to write out it a bit formally. So again, we'll just write out these statements that d of x1 and x2m is equal to d of x1 v1 plus d of v1 v2m plus d of v2m x2. We know that this thing is 1. Oh, this was 0, no? Yeah. It's fine. Okay. Nice. This is the distance between vx1 and x2, which by induction is 1. Yeah. And we have that also, we know initially by contradiction assumption that d of x2m and like d of x2m to and x2m plus 1 is also 1. So we'll write it out in terms of going down the branch and moving along the skeleton. x2m v2m plus d of x2m plus v2m plus v2m plus 1 side v2m plus 1 plus d of v2m plus 1 x2m plus 1 is also equal to 1. Now notice that, yeah, so if we add these, then sort of they magically cancel off, because we can ignore like this thing is repeated twice, this x2m and this 2m, so mod 2 it doesn't matter. And if I actually now look at d of x1 v1 and d of v1 v2m and v2m v2m plus 1. So by this path condition, we know that d of v1 v2m and d of v2m v2m plus 1 is actually d of v1 v2m plus 1, right? Mod 2. I ignored that.
Yes, we are not ignoring you.
Okay. So if you add these, then basically you'll get that d of x1 and v x2m plus 1 is equal to 0. And I guess you can do that for yourself like the other one, where like this we inducted showing or even, and then that implies the odd thing. And you can do it similarly for that even thing, and you'll get that d of. So in particular, this implies, this is also very clear to see if these were all collinear in a sense that they lied on a path, but since they were lying, they might lie on separate branches. So we need to deal with it a bit carefully, and that's why I had to work with this in mod 2, and then stuff happens. And so this basically implies that our original path, which was here, consisted of 2k plus 1 vertices, if I remember right, 2k plus 1 vertices. Then by induction, I'll get that this like x1, x2k plus 1 was a cycle, right? But I have on the spanning tree that d of x1, x2k plus 1 is even by induction, right? But this is a contradiction because x1 and x2k plus 1 are also directly connected outside the tree. So this is our desired rainbow cycle. Do people get it?
Yes.
So this might be a bit confusing with the notation, so I'll repeat it basically. So essentially what we did, we assumed we had a rainbow spanning tree, and then we noted that two consecutive things in the spanning tree, their distance cannot be even because we could just add that color which was outside the tree and there would be our cycle, odd cycle. So this thing was that, and this we basically used along with this good notion of distance along the branches and the skeleton to induct and get that between any x1 and odd vertex of that tree, we have that this is even, and for that even we know that this is odd. But basically we could do this till the end and get that x1 and x2k plus 1, the distance on the tree is even, but x1, x2k plus 1 is also an edge. So that would be a tree, and that would be a contradiction. So now the point is, this was all sort of what you can say wishful thinking because we don't have a rainbow tree. But till now you realize that there was no need of a rainbow tree, only like spanning tree. We don't necessarily have all n vertices covered in there. The only requirement for us was that we have a tree and we have a color which is not present as an edge in the tree, but has its odd cycle between the vertices in the tree, right? Hello.
Yeah.
Yeah. So this motivates us to algorithmically create a tree, which is why I took this problem in the lecture. So now we like, you can see clearly this entire thing that I did, all the requirement was there were some vertices which like all the edges were distinct colored, and there was one condition that there like some color was outside these, and they formed a odd cycle within vertices of this thing, and I could use the same argument there and get my thing. But yeah, and there, so now we algorithmically create a tree. Basically, we take one vertex, take one edge, distinct colored, add a vertex to it, keep on doing that, basically adding more vertices and adding new colors. So suppose at some point you cannot do it. So what must be your problem? So the problem might have been all the, let me draw some random. So suppose I have created this tree on my own, and till now we know all the edges are of different colors and we can't proceed further. Then what must be the problem that is happening? So any color that is any edge color that is present in the tree, so it's so basically, yeah, it is all that it is present. There is any cycle is there, it is already present, and you cannot extend it, because if a cycle extended to the outside, then there would have been some vertex set like in this set that was outside. Like these are the vertices that are outside of the tree that I have created till now. So there are some things that are preventing you, and basically that is the color. We look at a color which is not yet been added as an edge. So if it's cycle comprised of some vertices in here and some vertices in here, you would basically be able to find a vertex in here and a vertex in here, but then you could have extended your tree. So such a case doesn't happen, right? I guess I didn't say it really, but uh, the colors that form the edges of the tree, if like obviously there is if there is some extra color that also arises from some vertex in here, so either it forms its cycle completely in here, in which case we are already done by using using the argument we did previously, or its cycle involves some vertices in here and some vertices in here. But if it involves, then due to the
Then
fact
it would like not be an this these parts would be then connected, which is an
so
I guess.
like connected, or basically we could increase our tree by including this
Yes,
vertex.
yes.
So this case also doesn't happen. So it follows that no color forms a cycle inside this, and basically the only colors, yeah, like no extra color, and the only colors that are present in this group of vertices are the edge colors, right?
Yes.
So, but these are say k vertices, and there can be at most k minus 1 colors because of k minus 1 edges. But in that n minus k vertices, there are greater than n minus k colors. So we can induct. Similar to that connected component argument I showed in the beginning. Like not similar, but okay. Like, yeah, those cycles are completely present in this group. Colors are more than the number of vertices in here. So we can induct. Does everyone get it?
Yes.
Okay, I guess I had one more problem, but I guess most of you would have already seen it. Yeah, it was in the local unit.
But I guess it would go beyond the time.
Yeah, I guess yeah, we are also done with the time limit. So, Krutarth, you can stop the screen recording if you are present.